So here is the electromagnetic spectrum where we have frequencies ranging all the way from 0 to 10 to the power of 20. Typically, the frequencies that are used for communication range from around here to around here. So this is what is also represented here by this blue box, and this band goes by different names based on the frequency occupied. So waves from around 10 to the power of 3 to around 10 to the power of 7 are called radio waves. Beyond this are microwaves, infrared, visible, ultraviolet. So as I said, communication is focused within this band. Beyond this band, like X-ray and gamma rays, these are not used for communication because they are difficult to produce. It is difficult to embed information within them, and more importantly, they are harmful for humans. So what is also shown here is the approximate scale of wavelength of these waves. So in the radio waves, the wavelengths are about the size of buildings. Here about humans. As you go further up, you start hitting molecular levels. So this figure also shows the frequency ranges supported by different media. So here if you see, the twisted pair supports frequencies between 10 to the power of 4 all the way up to 10 to the power of 8. What this means is frequencies that are above this range are severely attenuated by twisted pair, and similarly frequencies below this range also cannot pass through twisted pair. So different media have different such characteristics. For example, a coaxial cable passes frequencies only between this range. Beyond this, it severely attenuates them. Fiber optics passes frequencies that are between 10 to the power of 14 to 10 to the power of 15. When it comes to wireless, everything is free space. In other words, you can send any waves you want. So what often happens there is the spectrum is divided into bands, and a given band is allocated for a particular service. So for example, you may decide to allocate this band, which is ranging from roughly around 10 to the power of 8 to 10 to the power of 9 to TV. In other words, the TV services, when they are using these waves for communication, will use frequencies that are within this band. Similarly, satellite will use within this band, and this is FM radio and this is AM radio. So this way you are avoiding interference between different services. Since each service has its own band, they are not going to interfere with each other. So let's quickly see the characteristics of some of the popular links. The twisted pair links is used in Ethernet as well as telephone lines. There are different categories here: Cat3, Cat5, Cat6. The categories are a function of how many twists you have per centimeter, as well as some inductance between the pairs and so on and so forth. So what is of relevant here is this, where this is the bandwidth of the link and this is the attenuation. So for example, Cat5 links have a bandwidth of about 100 megahertz and the suffer attenuation between 2 to 24 decibels per 100 meters. Now, why do you think this is a range? This is because different frequencies suffer from different attenuations. So lower frequencies suffer less attenuations, whereas higher frequencies suffer more attenuations. Typically, these cables are used under 100 meters. Why? We'll see the reasons for it shortly. And they support data rates between 10 megabits per second all the way to 1 gigabit per second. So next is coaxial cable. It's typically used in cable TV. It can provide up to 1 gigahertz bandwidth. And these also suffer attenuation ranging from 1 to 45 decibels per 100 meters, but for any given frequency, coaxial cable suffers less attenuation than twisted pair. These are used up to 500 meters and they provide data rates between 10 to 100 Mbps. Fiber optics are used in long haul transmissions. These are what form the internet backbone. They support frequencies that are in terahertz and their attenuation is extremely small, which is 0.2 decibels per kilometer. Remember earlier I was saying per 100 meters, whereas this is per kilometer. And they can go for long distances, tens of kilometers, and they can support extremely high rates up to 10 gigabits per second. So in terms of wireless, there are a whole range of usage: TV, satellite, cellular, Wi-Fi, WiMAX, so on and so forth. And spectrums can range from a few kilohertz to few hundred gigahertz. But actual allocated spectrum is a function of technology. For example, for Wi-Fi, 40 megahertz is used for transmission purposes. And for LTE, which is the cellular, advanced cellular technology, 20 megahertz is used for a particular transmission. And how much attenuation they suffer, naturally this is going to be a function of the buildings, the trees that block the propagation of the waves. But if it were free space where there is no obstruction, this is a formula that gives the loss they suffer as a function of distance. For example, at 1 kilometer and 100 megahertz, the loss is about 74 decibels after 1 kilometer, and similarly at 1 gigahertz the loss is about 94 decibels. You can cover distances from a few meters to few kilometers, and the data rates you can support are range from few this should have been few kilobits to hundreds of megabits per second. So links are also classified based on how they support data flows. For example, full duplex links support data flow in either direction. This they achieve mainly through using two pairs of wires, one for each direction. Half duplex links support data flow in only one direction at a time. The way you can relate to this is through a walkie-talkie. In walkie-talkies, you talk, stop, and then provide an opportunity for the other person to talk. In other words, two people cannot talk at the same time. Now in simplex links, you support unidirectional communication permanently. In other words, you cannot have data flow in from the other direction. This is not permitted. You only permit data flow in only one direction. The way to relate to them is through a one-way street. So a quick summary of what we have seen in this video. There are two components at the physical layer. One is node, another is link. Within a node, we looked at the hardware, how the software is organized, and how we move data from the memory to the adapter. We also studied about links, which basically carry electromagnetic waves. We saw how links can be imperfect, they can attenuate, they can cause delay distortion, they introduce noise. And we also looked at spectrum, that is the bandwidth of these links, and also studied different types of links: twisted pair, coaxial cable, full duplex, half duplex, so on and so forth. So going ahead, we will see how we can transform the data to signals which are in turn carried by these links.